Hey, Castle here, and welcome back to Memphis Communiversity. Today we are going to be talking about indefinite integration, or U-subs. And I call this U-subs because U-sub is the process by which we are going to work through these indefinite integrals. And I'm going to go through 5 steps of the process. All the steps kind of flow together, and it comes a lot more naturally the more practice you do. So we're going to go through a lot of example problems. As always, this worksheet is in the description below as well as the answers, so you can download that and work alongside with me. So let's just get started with the U-subs. What we're looking at is indefinite integrals, which are those integrals that don't have numbers. And if you remember, that always means that we're going to put a plus c at the end if you've seen any of these other videos. If you don't know that, you'll learn it. And what we're trying to do is basically take these pretty tricky indefinite integrals and just turn them into something a lot simpler and a lot easier to work with. And so the way that we're doing that is through this U-sub process, which is kind of like the opposite of the chain rule. So we're going to be identifying a U as our first step. So the way that we identify the U is, what I think of it is kind of like an inside function. We talk about inside functions sometimes. For me, that just means something that is kind of on the inside of this pretty long function. In this case, we have x to the 4 plus 2 inside parentheses and also inside an exponent. So I consider that kind of an inside function. Another way that you can identify in the u in these problems is you're looking for something whose derivative actually kind of shows up somewhere else. So in this case, that x to the 4, the derivative of that is 4x cubed, which shows up right here. And you'll see as we work through these problems why that's important and why it's helpful. The exact derivative of the u might not always show up, but it will be something similar. So I'll keep pointing that out as we work through them. So our first step is to find the u, and like I said, it's that kind of innermost function that's inside the parentheses, x to the 4 plus 2. So I'm going to write that down. Every time I do these problems, I'm going to write the first two things together and kind of keep them separate from the rest of my work so that I don't get mixed up. Because the second thing is to take the derivative of that u that we found. So again, the u is kind of just something, a letter that represents a longer function. So instead of using that really long function, we're simplifying this integral by using a u instead. And you'll see how it becomes simpler as we work through it. So the derivative of that is 4x cubed d of x. And when I do these problems, I'm going to try to, in this case, I'm isolating that x. So I am going to move on to step 3 now. So step 3 is we're going to rewrite the integral, but instead of using x's, we're going to use our u that we found. And I'm just going to go ahead and finish writing these steps. So what I did is I divided that du by dx to isolate the 4x cubed. And as we rewrite the integral, you'll see why that's helpful. And you can do that in your head as we get more practice, but I'm always just going to write it all out. Okay, so I've written out all the 5 steps. Again, they all kind of flow together, and I'll show you, especially on this first problem, where each step comes into play. But what I'm doing now is that third step, and I did integral u to the 7. As you can see, since I have this 4x cubed right here, it actually cancels out with the 4x cubed that's in that original integral. And let's see. What I should have done here, I didn't show all my work, is divided du by 4x cubed. In all the other problems, I'll show it like that, where you isolate dx. Isolating dx usually gives something that you can work with that's going to cancel out with something in the original so that you don't have to worry about a coefficient in front of that integral, and it just becomes even simpler. So in this case, if I had divided that du by 4x cubed, I would be left with a coefficient of 1 over 4x cubed, which cancels out with that in the original. And my new integral with the u, not with the x's, is integral u to the 7 du. So now I'm going to do that fourth step, integrate plus c. So I just integrated with the u using the power rule and got u to the 8 over 8 plus c because it's indefinite. And then my final step is I'm going to go back in, and after I've integrated with the u, I'm going to substitute back in whatever my u was using x's. So I substituted back in the x to the 4 plus 2 to the 8 over 8 plus c, and that's my answer. And if that one was a little confusing, again, we are about to do a lot of practice. So what I'm doing now is kind of just marking up each of the steps. I found my u, I found my du, I rewrote my integral with the u, integrate plus c is step 4, and step 5 is to replace back in that x. So let's move on to number 2. Okay, so again, we're just going to follow these 5 steps as we do the second one. The u is pretty similar to the first one. It's just inside parentheses and also inside an exponent. So it's pretty clear that the u is 8 minus 4x. Our du is going to be negative 4 dx. And then I'll show my work here where I'm dividing du by dx to get negative 4. And let's see. Okay, so now I'm showing you where I isolate dx. That's always what you want to do. And you're going to isolate dx by dividing du by whatever was on that side with the dx. So then, as you can see, because we've got our dx isolated, my coefficient of the new integral is going to be negative 1/4. And I don't see anything here that the negative 1/4 can cancel with. So we just have to keep that when we do step 3, which is rewriting the integral using our u. So I'm going to have that negative 1/4. And that comes from there. And then I have my integral u, and I've got to the 15th because that's still there. And then just like on that first one, when I integrate this, I'm still going to be using the power rule, doing a pretty simple integral because all I have is u to the 15. So I've got negative 1/4, I've got to keep that there, times the integral of u to the 15, which is u to the 16 over 16, plus c because it's indefinite. And what I'm doing now is step 5, where I'm substituting back in that x for the u. So that one's pretty similar to the first problem. Okay, so let's move on to number 3. The u here, again, is pretty clear because we've got it inside parentheses. Our u is usually our innermost function. So we've got u is pi t, and du, now instead of dealing with x's, we're dealing with t's, which doesn't change anything. It's just a different variable. So we've got pi d of t. I'm going to isolate d of t by dividing d of u by pi. So then I've got that 1 over pi as my coefficient for the new integral because that 1 over pi doesn't cancel with anything in the original. So we are going to substitute in our u. I've got 1 over pi integral sine u d of u. And now I'm doing my step 4, which is integrate plus c. So remember the integral of sine u is negative cosine u. You've got to remember that negative and keep up with it. And we've got to also keep up with that coefficient, that 1 over pi. And so now we're just doing step 5, putting back in our original u, which is pi t, and keeping that plus c the same. So again, another pretty simple u sub. It's just a matter of following those 5 steps, making sure you keep up with all the negatives, and make sure you have that plus c every time. Okay, so on this fourth one, finding the u can be a little bit more tricky on this one. I'm just going to circle my u's from the other problems. So our u here is just the 10 minus 7x, and you might want to think that the u is 1 over 10 minus 7x because that 10 minus 7x is on the bottom. But something that's kind of helpful as you choose your u, if you're not sure exactly what it is to think about what it would look like to continue the problem with the u that you chose. So in this case, if I had chosen the u as 1 over 10 minus 7x, it would turn into an incredibly complicated problem. And it's usually a lot more simple than that. A lot of the times you have things cancel out because your whole purpose of this is changing a really complicated integral to a really simple one. So if the u that you chose is just making things a lot more complicated for you, then you want to try something different. So in this case, we've got 10 minus 7x as our u. Our du is going to be negative 7d of x. And we're going to isolate that d of x. Sorry, my hair is kind of coming into the screen here. Don't worry about that. So we isolate the d of x, we're going to get negative du over 7. So that negative 1/7 right there is going to go before our integral. And now we're doing our integral with our u. So I've got du over u Make sure you don't forget that du on the top. And then when we integrate that, remember that 1 over u is going to be ln of u. Make sure you remember your plus c because it's indefinite. And then we're just going to go ahead and put back in our 10 minus 7x for step 5. And since it's an ln, I put it in absolute value bars. Okay, so number 5, our u is pretty clear here. We've got it in parentheses. It's to an exponent, so I'm going to write that out. U equals 2x minus 1. And then our du is going to be 2 dx. So it's pretty easy to isolate this d of x here. You're just going to divide du by 2. And we've got that little 1/2 there that we can't forget about. So we have to put 1/2 before our new integral. And since that 1/2 is going to be multiplied by the 3 on the top, I just went ahead and wrote 3/2 to keep everything outside the integral so that integrating it is as simple as possible. So remember that, I'm going to pause this. Okay, remember that when you have your u, that makes things a lot more simple, but you can't forget about the other things in the original problem because you might have numbers that aren't a part of your u that you can't leave out. So in this case, that 3 might be easy to forget. You might be tempted to just write 1 over u to the 1/4, but you've got to remember that 3. So here I just put it with that 1/2 outside the integral. And I wrote this as u to the negative 1/4 just to make things easier when I'm integrating. Du equals 3/2 times 4/3 u to the 3/4. That's the power rule that I'm using, plus c, and then I'm going to plug that 2x minus 1 back in for u. Okay, so let's move on to number 6. So number 6 is an example of when I was talking about how the u sometimes is a little clearer if you realize that its derivative actually shows up somewhere else in this problem. So in this case, if we're trying to decide on our u, if you look at ln x right here, you know that the derivative of ln x is 1 over x, and you can see 1 over x in this problem. So that's a sign that that might be our u, because again, we want to be able to cancel things out whenever possible, and if the derivative of u shows up somewhere in the problem, then we're probably going to be able to cancel out some x's, which is always good because it makes things simpler. So I'm going to choose ln x as my u, and then my du is going to be 1 over x. But again, we are going to isolate dx every time we take the derivative of u, and when we isolate dx, we are going to end up with x, which cancels out with that 1 over x right there. So then we end up with just du over u as our new integral. I didn't show my work for isolating that dx, but you always want to either write it out or do it in your head because you're always looking for things that can simplify. So I took that integral with the u, and then I went back in, plugged in my original. So it looks a little funky, but there's your answer. It's ln of x plus c. Okay, let's move on to number 7. All right, on number 7, those parentheses, that exponent, those are all clues that our u is going to be ln of x because it's inside other functions. So we also have that 1 over x that shows up somewhere else in the problem. And remember, just like on the previous one, the derivative of ln of x is 1 over x. And since it shows up, that's another clue that that's our u. So our du is dx over x. Again, if we isolated d of x, we would end up with a number that cancels with that 1 over x, so that makes things a lot simpler for us. And our integral is just going to be let me rewrite that. Our integral is going to be u squared du, because that x cancels. And so then when we do the power rule on that one, we're going to get u to the 3 over 3 plus c, and then we just take that ln of x that we used for u, plug it back in for where that u was, don't forget your plus c, and there is your answer. Okay, finding the u on number 8 might seem a little bit more tricky, but again, we've got an inside function up here. It's in an exponent, and it's an exponent in itself. And then, like I said, the derivative of your u is going to, a lot of the times, kind of show up somewhere in the problem. And since the derivative of that u is negative 2x, if my finger's not covering it, even though you don't exactly see a negative 2x, you have an x in this problem, and so that's kind of a way that it shows up because you know you're going to be able to cancel that x with something later on in the problem. So let's use that negative x squared as our u, and then our du is going to be negative 2x dx. And I'm going to show my work for isolating the dx this time. So I would get x dx equals negative du over 2. I'm keeping all my x's on this side and everything else on this side. So then I'm going to isolate a little bit more. Oh, I'm not showing the isolation work here. I'm just going to take that negative 1/2 and I put it before the integral right here. So don't forget that 1/2. And then I'm going to have e to the u, because that's where our u was, du. And so now I'm integrating that using our u. So I'd get negative 1/2 e to the u plus c. And then I'm going to go and plug back in that negative x squared. And there's my answer. Okay, number 9 is another one where finding the u, it's a lot easier if you kind of recognize the derivative somewhere else in the problem. In this case, if you remember that the derivative of secant x is secant x tan x, then it's easier to choose that secant x as your u, but it's also inside a square root, so that's another hint that it's your u. So I'm going to take that u, take the derivative, dx, and if I isolate dx here, then I would get 1 over secant x tan x, which cancels with this secant x tan x and makes things a lot easier for us. So I'm going to do my integral, square root of u, du, and that could also be written as u to the 1/2 du. So I kind of just did that in my head, did the power rule here to get 2/3 u to the 3/2 plus c, and then I'm plugging back in that secant x to finish it off. Okay, let's move on to the back of the worksheet. Okay, I rewrote the rules on the side for you to kind of refer to as we do these next few, just to refresh your memory of what they are. But hopefully, now that we're doing more practice, they're kind of all going together for you, and it's just one process instead of kind of thinking it as all these different steps, because they all really do go together. Okay, you cannot see what I'm doing up there, but what I did was I took that sine 8 of theta. Oh, my hand is in the way now. Okay, I took that sine 8 of theta that's in the problem, and I just rewrote it as sine theta of 8, and that helps me recognize sine theta as my u because it's inside that 8 exponent. And again, the derivative of sine of theta is cosine of theta, which shows up here. So that's a hint that that's our u because we want something that we can end up canceling as we do the problem. So I've got my u, I'm doing my du is cosine of theta, d of x, or d of theta. And if I isolate that d of theta, I'm going to get 1 over cosine theta, well, du over cosine theta technically, but that 1 over cosine theta is going to cancel with this cosine theta in the original and make things simpler for us. So now that we have that canceled, our integral is just going to be integral u to the 8, which is a pretty simple one. We're going to use power rule for this one as we integrate, and we're going to get u to the 9 over 9 plus c. And then we take that sine theta, that was our u, and plug it back in as our 5th step in the process. All right, let's move on to number 11. Okay, number 11 looks a little bit daunting because we have c's and b's and x, but it's not too bad because we're going to have things that are canceling out. So we're going to take that inside function, that cx squared plus bx to the 4, and that's going to be our u. It's inside the square root, so that's our hint that it's the u. And the du is going to be 2cx plus 4bx cubed times d of x And so what I'm doing now is I'm going to isolate that d of x by dividing du by 2, because 2 is our common factor in these two different functions. So then I'm going to get du over 2 equals cx plus 2bx cubed, and that shows up right there. So those are going to cancel out. Yay. And now we've got a much easier integral. You've got that 1/2 that you take from the du over 2, put it in front of the integral. That cx plus 2bx cubed is going to cancel with the top here, making things easier for us. And you've got u, I wrote it as u to the negative 1/2. It could be written as 1 over square root of u, but writing it that way just makes it easier to integrate. And you're going to integrate using the power rule to get 1/2 times 2u to the 1/2 plus c. And then as our last step, we are going to take our u that, let's see, okay, we're going to take that cx squared plus bx to the 4 and put it where our u was. And I didn't show all my work here, but I'm just rewriting it as square root of all of that plus c. All right. Number 12 is a tricky one, and it's a lot different from all the other ones here because this actually isn't a normal u-sub problem. This is a split numerator. So in this case, all you have at the bottom is an x, and then at the top you have a subtraction function. So you can actually split this integral up, and it turns into something a lot easier than a u-sub actually. So if you can recognize this as a split numerator, that makes things a lot easier for you. So since we've got just that x on the bottom, we can actually split it up to integral of 17 over x minus 1, because that x over x is just 1. So now we've actually got a pretty easy integral that we can work with. So we're going to have dx equals 17 ln x, because of that 17 over x, that's the derivative, minus x, because that's the derivative of that negative 1, plus c. So that's actually not a u-sub, that's a split numerator. It's just tricky because sometimes those ones look like u-subs. But again, if you try to make this into a u-sub, it'll be way more complicated than it should be. And this can be something that you have in the back of your mind and think, okay, if this u-sub is completely way too complicated for me, maybe it's a split numerator, because that makes things much easier. Okay. Number 13 is a little bit tricky too, because you have to remember some of those more specific derivatives that you've learned maybe a long time ago. So the derivative that I noticed here is that the derivative of inverse secant x is 1 over square root, or 1 over x square root of x squared minus 1. And like we did on some of these earlier ones, sometimes your u is the thing whose derivative shows up somewhere else in the problem, which you can see here. So we're going to use that as our u, secant, inverse secant of x, and then our du is going to be all of that I just mentioned that hopefully you have memorized. And then again, when you isolate your d of x and do that multiplication there, you're going to end up with a number that actually cancels out with this x square root of x squared minus 1. It's a lot. That's going to end up canceling out, and you actually end up with a much, much easier integral once you do that. So now our integral is just going to be du over u. And when I integrate that 1 over u is going to be ln u plus c. And so at the very end, that step 5 is going to be taking the inverse secant of x, putting it where your u is, and there's your answer. Okay, number 14 looks a little tricky because you just have a lot going on there, but I think the best way to start this is to rewrite, or at least in your head kind of rewrite, that sine pi over x squared as over x cubed as sine pi over x squared times x to the negative 3. Just because that's something that's a lot better to work with when you're integrating. So my u is going to be that inside function that I've got I made my u pi x to the negative 2 because from this that I rewrote, I canceled out those exponents to give myself a much simpler pi x to the negative 2. And so I'm going to be using that, and my derivative is going to be negative 2 pi x to the negative 3 d of x. And then I'm simplifying that. I'm isolating that dx as much as I can. I've got to keep my x's on one side. And then that's going to be negative du over 2 pi. So then my integral, oops, I forgot that coefficient. Oh. There it is. Okay, so there's my coefficient, that negative 1 over 2 pi that I've got. And then I'm going to be rewriting this integral as sine u du. Remember that you've got to have that sign. Because the sign's not part of your u, you have to keep it when you rewrite your integral. And so integrating that, I'm going to get 1 over 2 pi times cosine u. I took away the negative from the 1 over 2 pi and the negative from changing sine into negative cosine, cancel each other out, so I've just got a positive there. And then I substituted back in all my x's for my u and kept my plus c, and there's my answer. All right, number 15. Okay, number 15's another one kind of like number 13, where you have to just know your derivatives. So you can kind of see that that inverse sine is similar to the inverse secant that we did on number 13. And we know that inverse sine, hopefully we know that inverse sine is 1 over square root of 1 minus x squared. And that shows up again somewhere in the problem, which means that we're going to be able to cancel at some point, which is great news. So our u is that inverse sine of x, du is dx over square root 1 minus x squared. Again, if you isolate dx, you're going to end up with something that cancels out with that square root of 1 minus x squared on the bottom, making our integral super simple. It's just u du, which using the power rule is going to be u squared over 2 plus c. And then we take that inverse sine of x and put it back where our u was. Don't forget the plus c, and there's your answer. Okay, number 16 is another one where it looks a little bit tricky to choose our u, but again, if you see parentheses, that's a big hint that you've got a u. So we're going to take that 4t and use that as our u. The derivative of that is a trickier derivative. Remember that ln of x ends up being ln of, hey, sorry about that. So like I was saying, that u is 4 to the t, and the derivative of, I meant to say a to the t is going to be, or a to the x is going to be ln of a times a to the x. So there's our derivative. And then you've got du over ln of 4 equals 4t d to the t if you've got your t's on this side and the rest on this side. So you're going to be left with that 1 over ln of 4 as your coefficient before the integral, but that 4 to the t is going to cancel with the 4 to the t in the original, leaving you with that integral secant squared u d of u. Keep that 1 over ln 4. Don't lose that when you do your integration. And you know that the derivative, or the integral of secant squared u is tan u. And we're going to take that u and that 4t that we used as our u, put the 4t back in the place of the u, remember our plus c, and that is our answer. Okay. So these last three problems are all a little bit tricky. You won't see them very much, but we need to make sure that we are familiar with them. Okay. So number 17, I'm going to start with 2 minus x as my u. And then the derivative of that is negative dx. So if we isolate our dx, we end up with negative du right there. So we have to keep up with that little negative. Make sure you don't lose that as you're moving on to the next step, which is our integral. So we've got negative integral 6 minus 3u over u. Okay, so the reason that number 17 is a little bit different is because it's kind of like number 12, where we didn't actually have a u sub, we just had a split numerator, and it's something that you just have to notice. So this actually looks pretty similar to number 17. We've got a single variable on the bottom, that u, and then we've got a subtraction function on the top. So let's just treat this as a split numerator and see what happens. So I'm going to take those and split them up and be left with negative integral 6 over u minus 3, because those u's cancel out. You don't have to worry about writing those. And so we've got a split numerator here, but we still have a u in the problem, which means this is actually going to be kind of a double u sub. So when I take the integral using the u, I'll get negative 6 ln of u minus 3u plus c. And we don't want to be left with u's at the end, so we're going to take our original 2 minus x from earlier and plug it in. And there's our answer. Okay, number 18 is kind of a doozy as well, but what I'm going to do is rewrite this integral as cosecant x to the 3, or cubed, so that I can recognize that u as cosecant x, and then take the derivative of u. Again, this one's just kind of crazy because the derivatives are so long, it's easy to get things mixed up. Make sure that you hold on to that negative, since you've got that cosecant. You've got to have a negative when you take the derivative. So right here, I'm just isolating my dx, or I'm isolating all my x's, keeping them on one side, and taking that negative to the du. So as you can see, that cosecant x cotan x is actually going to cancel with some of the stuff in here, not all of it. You're still going to be left with a squared right there, but the cosecant x cancels with one of those cosecant x, and then the cotan x cancels. You've got to hold on to that negative, don't forget that, and then you'll be left with negative integral u squared du. Use the power rule when you integrate that, and don't forget your plus c as always. And then go ahead and take that cosecant x and put it where your u was, and there is your answer on that one. So that one's just kind of a tricky one, because you have to see what cancels out, and you've got to kind of break up things and make sure that you hold on to little things like the negative or like that squared. Make sure you wouldn't have u cubed. That's something that would be easy to do if you miss the fact that this cosecant x cancels and turns this into cosecant squared x. So let's move on to number 19. This is a big one because it's going to end up being a double u sub, so it's hard to keep up with all the stuff that you're doing, but we can do it. It's going to take up a lot of room, and it's going to get really crowded down here, so bear with me. Okay, so our first u is going to be the innermost function, which in this case is going to be that cosine 2x. Let me pull up my other video. Alright, so we've got that cosine 2x. Since that's the exponent of the e on the bottom of this function, that's kind of our innermost function. And again, that derivative of cosine 2x is sine, or negative 2 sine of 2x, and you see a sine 2x actually shows up earlier in this problem. So that's going to give us a hint that that is our u, or our first u. So then you're going to keep all your x's on one side and be left with negative d over 2 equals sine 2x dx. You can see that that sine 2x is going to cancel with the sine 2x up here when we write our new integral, but the negative 1/2 doesn't cancel anything, so you have to keep that in front of the integral. So I'm going to have negative 1/2 integral e to the negative u, don't forget that negative when you do it, du. So we've still got a u in there, so that means that we're going to have to do u sub again, kind of like on number 17. So our u in this case, and okay, let me clarify. So we're doing a double u sub, and because we're doing the u sub a second time, we don't want to get the u's from our second u sub confused with the ones from our first one. So instead of using u and du, as I'm doing it this second time, I'm just going to use v and dv. That might be a little bit confusing if your U's kind of look like V's. It can really be any letter. I just chose V because my V's and my U's look pretty different. But as long as you use something to distinguish your second U sub from your first one, doesn't matter what the letter is. So I'm going to take that negative U right there, and that's going to be my V, which is kind of just like my second U. And then the derivative of that is just negative du. So again, the purpose is to make things simpler, and although this problem is pretty complicated, using U subs actually does make it a lot simpler and a lot easier to work with. I'm going to move my face up here so you can see the work that I'm doing. So I just took that negative 1/2 integral e to the negative u du. I was just rewriting it there. And using my new v and dv, I'm going to turn that into 1/2 because I've got that negative right there. The du is negative dv, so that negative cancels with that one. And I'm going to have ev instead of e to the negative u because our v is negative u. And that's going to, when I integrate, that's going to be 1/2 ev because the integral of e to the v is just e to the v plus c. And then I'm moving all my work up here because I ran out of room. I'll move myself back down here. But that is just going to be 1/2 e to the negative u plus c. And I'm going to simplify it even more, making it 1/2 e to the negative cosine 2x plus c, because in our final answer we can't have any u's, we have to have all x's. So we are finally done with that problem, and we are done with the worksheet. So thank you for listening. I hope that you'll go watch other videos on this. Make sure you keep getting a lot of practice because U subs are very important. But the more practice you do, the easier they become. Those last few I know were pretty tricky, but most of them are more like the first 15 or so that we did that are a lot simpler. So I hope this was helpful, and I hope you check out the other videos on Memphis Communiversity. Thanks for listening. Bye.